right. Hi, my name is Amy. This is research titled Multi-Spacecraft Wake Formations by myself and my colleague Kaylee Champion. The motivation for this work is the electrostatic tractor, which is a concept for contactless debris removal in GEO. The way this works is a servicer spacecraft is equipped with an electron beam, and it aims that electron beam at a target debris object. Now, the target debris object is being bombarded with electrons, so it charges negatively, while the servicer is losing electrons, so it charges positively. So you have a negatively charged object and a positively charged object. So the result is an attractive electrostatic force between the two spacecraft that allows the servicer to pull the debris into a graveyard orbit. The electrostatic tractor concept has been studied extensively in GEO because charging in GEO is easy. The debye length is on the order of 100s of meters, which makes it possible to keep a suitable distance between the spacecraft during the tugging process. However, in other regions of space, this isn't the case. In cislunar space, the debye length can be as low as 10 meters, and in LEO, the debye length can be only on the order of centimeters. However, in both of these regions, the spacecraft might be mesothermal to the ambient plasma, which means that there could be an ion-depleted wake on the anti-velocity side of the spacecraft. So the idea here is that maybe we can use electrostatic tractor concepts in cislunar space and in LEO by charging within the wake of the servicer. And this is a really interesting concept, not just for active debris removal, but it could also be promising for anything that would require electrostatic actuation, like proximity operations, for docking, for manufacturing. But because the target is charged negatively and the plasma wake boundary is full of these positively charged ions, the question is, how will the plasma wake respond to the charged target within it? So I'm going to start by talking about cislunar wakes. Cislunar wakes form in two different regions of cislunar space. They form in the solar winds and in the magnetosheath. Something else that's really interesting about cislunar wakes is that they always form on the side opposite of the solar winds. This seems a little bit counterintuitive because when we think about wakes like behind the boats, they form on the anti-velocity side of the spacecraft. But in cislunar space, that's not the case. And that is because the solar wind is really, really quick. It moves at 400 to 900 kilometers per second, while the spacecraft velocity is only around 1 kilometer per second. So we simulated cislunar wakes using SPEACE in the solar winds, using average solar wind conditions. So the plasma density was about 10 to the 6 particles per meter cubed. We used Maxwell-Boltzmann electrons and peak ions, and we used the debye lengths to come up with suitable resolutions for both the spacecraft and the boundary mesh. As you can see, we generated a whole bunch of different results for cislunar space. What this slide is trying to show is the wake collapse for different servicer to target radius ratios as the target charges. So when I say servicer to target radius ratios, I'm really talking about increasing the size of the target, which is the smaller sphere in the wake of the larger sphere. So the servicer stays the same size. The servicer is always 2 meters. But for the 8:1 ratio, the target is 1/4 of a meter. For the 4:1 ratio, it's 1/2 a meter radius. And for the 2:1 ratio, it's a 1 meter radius. On the columns, you can see the different electric potentials of the target. So there's uncharged 0 volts. Then we have -10 kilovolts, -30 kilovolts, and -40 kilovolts. Here on the slide, you can see that by -30 kilovolts, the wake has essentially collapsed for all 3 different radii. But for -10 kilovolts, the wake has only begun to collapse for the larger spheres. And so this is better illustrated in this plot here, which shows the ion current density as a function of the target electric potential. So initially, when the target is uncharged, there's no ion current density, which makes sense because it should be within the wake. The wake should be existing properly, and there are no ions within the wake, so there should be no ion current. But as the spacecraft begin to charge, they begin to collect an ion current, and that happens sooner at lower potentials for the 1 meter target than it does for the half-meter target than it does for the quarter-meter target. So basically, the larger targets collect ion currents at smaller surface potentials. Something else that was really interesting for cislunar wakes is that the wake collapse begins for the same potential field around the target for all three different scenarios. This is a super interesting finding because it means that it creates a good baseline for coming up with a model for the wake collapse and coming up with a model for predicting that wake collapse. Okay, so now I'm going to move on and talk about LEO wakes. So again, we simulated LEO wakes in space. Here we use solar minimum LEO conditions. And basically that is like the least dense that LEO can possibly be. But it's still really dense compared to cislunar space. The plasma density here is 10 to the 10 particles per meter cubed, which is 4 orders of magnitude larger than it was for cislunar space, which had a density of 10 to the 6 particles per meter cubed. Again, we're using Maxwell Boltzmann electrons, peak ions, and you'll notice that the resolution on the boundaries doesn't match the Debye length as well as it did for cislunar space. And we did try a finer mesh, but ultimately the results were the same and it just took way longer to generate. So we decided to go with the more coarse mesh. You can immediately see that we didn't do as many scenarios for LEO as we did for cislunar space. And that's because even for a 10 to 1 surface to target radius ratio, the wake collapses almost as soon as charging begins. So here I'm showing potentials uncharged again, 0 volts, 5 volts, 10 volts, and 500 volts. And this should all be minus signs, actually. And so if you look at these pictures, you'll see that 0 volts, we're safely within the wake. At 5 volts, the wake has started to move, and at 10 volts, the wake has collapsed. And at 500 volts, it just put it in there for fun, so you can see what it looks like when the wake has just like completely collapsed. Now remember, this is the order of volts, whereas in cislunar space, we were collapsing on the order of kilovolts, tens of kilovolts. So it's a pretty big difference. So again, this plot is very similar to the one I was showing before for cislunar space with the ion current versus the potential. But what I want to point out here is that if you pay attention to the values on the y-axis for that ion current, you'll see that they're actually 3 orders of magnitude larger for LEO than they are for cislunar space. Here we're on the order of milliamps. In cislunar space, we were on the order of microamps. So this makes sense, right? Because the ion density in LEO is so much higher than it is for cislunar space. But the reason I want to point this out is because if you think that these values look like they might be comparable to cislunar space, they're not. The ion current is so much higher in LEO than it is in cislunar space. So if you look at the red line, which shows the results for the target behind the servicer, as the potential increases, you can see that the wake collapses immediately at 10 volts. Something else that's really interesting for LEO is that having the servicer there actually makes a really big difference in the collected ion currents. Whereas for cislunar space, it made a little bit of a difference. Like there was a higher current for not having the servicer there, just for like being there in the plasma. But it makes a much bigger difference in LEO. And again, that's due to the ion density in the ambient plasma being a lot higher. Okay, so to conclude, and really just to summarize the findings, in cislunar space, wake collapse begins at a lower potential for larger target radii compared to the size of the wake. So if the target is closer to the boundaries of the wake, it begins to attract ions sooner, and that totally makes sense. And the other really interesting finding that can help with future models for predicting wake collapse is knowing that the potential field at the point of wake collapse is the same regardless of the target radius compared to the size of the wake. Now, in LEO, we found that the wake collapse occurs almost immediately as soon as charging begins, which means that electrostatic actuation operations would be extremely difficult if they even are possible in LEO. Kaylee and I are planning on doing experiments in our vacuum chamber that we have in our lab to get more results for both of these environments and see if, if the results are similar to what we're seeing in space or not. So yeah, so anyway, thank you for listening to my talk. And if you have any questions, you can send me an email at amy.haft@colorado.edu, or you can email my colleague Kaylee. Her email is also listed.